Hi. So over here again, we need to look at more examples to determine some of the reactions that's a bit tricky in the electrophilic substitution of benzene. Now again, we have two sets of reagents, set 1 being chlorine in a hydrogen carrier, aluminium chloride, anhydrous. Set 2, we have a methyl chloride in the presence of another halogen carrier, aluminum chloride. In this case, we can replace this halogen carrier with FeCl3. It works perfectly fine. They have the same function. So do not worry too much if I use Al or Fe, it doesn't matter. Let's say we start with benzene. Sometimes you notice that I put alternating pi bonds here, and sometimes I put the circle. Again, for this part, it does not matter because here I'm showing that there's a resonance of the pi electrons within the ring. Here I'm just showing that right now the pi electrons is between these two carbons. And since mechanism is not being asked, so we do not have to show exactly this structure. But if you are asked to give the mechanism to explain why a phenomenon exists, then this is the best one and not this. So let's start. From a benzene, let's say we add chlorine first. Electrophilic substitution. Okay, Cl2, AlCl3. Again, there's only one possibility here, chlorine. That's it. Now, then we follow by adding the methyl group inside there. And chlorine is a halogen with lone pair of electrons. So this must be 2,4 directing. So auto and para directing. That means the next compound would have two isomers, CH3, Cl, or the para isomer. Right? Cl and CH3. Okay? If I try the other order, and I put my methyl first, what you see is you first form a methyl benzene, then methyl group is electron donating. Inductive effect, it will force the next guy to go into the ortho or para position. So if you think fast, you will realize that I get the same molecule. Both will be identical. Now the next question is, so does it matter in this case, we add set 1 first and then set B, or 2 and then 1, or is both the same? We have to consider higher order thinking. Now there's some difference between these two intermediate we have in our synthesis, a chlorobenzene and methylbenzene. The main difference is a chlorobenzene is not so reactive compared to a methylbenzene. So why does it matter? We know that after we form this methylbenzene here, some of the reagent could still react with my product, because now methylbenzene's benzene ring here is more electron rich than before due to the presence of a methyl group, which enforces more electron density to the ring. It's more likely is activated to be substituted by a further electrophile. Whereas here the chlorine is deactivating. Electronegative pull electrons away, so now this product is less reactive than before. Which means to say that this methylbenzene could be further methylated as a side reaction that we cannot control to form a 1,2 dimethylbenzene or 1,4 dimethylbenzene. And if this happens, we could not get the same product as we wanted to get just now. For chlorobenzene, this has no issue, because after that, the first step, this is not so reactive. The chlorine will not react with the chlorobenzene, and it will stay as a mono-substituted product. And after that, you push it to put in the methyl group, you get the product. So in this case, it's very good for you to consider which is the better order and why this is so. Now you might be thinking, I know what you're thinking, that after you form a 1,2-dimethyl benzene, it is even more activated, right? More electron rich. You are absolutely right. So if I form this, there's a chance that you could even form more methyl groups into the ring, tri-substituted, tetra-substituted, or poly-substituted. So now we know that for this case, maybe the top pathway is better.